46 years after launch, a one-ton machine built with 170s electronics is still talking to Earth from more than 24 billion kilometers away. And lately, it's been talking nonsense. Voyager 1, humanity's most distant spacecraft, is sending back data that says its attitude control system is fine, while other instruments quietly scream, "No, it isn't." The numbers don't match, the signals look corrupted. Yet the spacecraft keeps flying, powered by a nuclear heart that's slowly dying. Engineers can't go there. They can only whisper radio commands into the dark and wait 45 hours for a reply. Somewhere beyond the edge of the solar system, something is going wrong, and nobody is completely sure why. To understand why this is so eerie, you need to know what Voyager 1 actually is. Launched in 1977, it's a bus-sized probe with a 3.7-meter high-gain antenna, 3 radioisotope thermoelectric generators, or RTGs, and a suite of instruments designed to study the outer planets and the space beyond. It weighs about 825 kilograms, runs on less power than a household hairdryer, and stores data on an 8-track tape recorder. Its main computer has about 68 kilobytes of memory. Yet this relic is now our only functioning spacecraft in true interstellar space, beyond the Sun's protective bubble. Voyager 1's original mission was a grand tour. Jupiter in 1979, Saturn in 1980, then a gravity assist that flung it up and out of the solar system at about 17 kilometers per second. After the planetary flybys, NASA repurposed it as a deep space observatory. Its instruments include magnetometers to measure magnetic fields, plasma detectors to sample charged particles, and cosmic ray detectors to count high-energy particles from distant astrophysical sources. It also carries the famous Golden Record, a copper phonograph with sounds and images of Earth, bolted to the side like a message in a bottle for any civilization that might someday find it, millions of years from now. So what does it mean that Voyager 1 is sending strange data? The problem centers on a subsystem called the Attitude Articulation and Control System, or AACS. This is the part that keeps the spacecraft pointed correctly, especially its big dish antenna aimed precisely at Earth. In 2022, engineers noticed that the AACS telemetry suddenly became garbled. Status readings were inconsistent, as if the system was reporting its health through a funhouse mirror. Yet the radio signal remained strong and stable, and the spacecraft still seemed to be pointing accurately. It was like a patient whose vital signs monitor shows chaos, while the patient calmly sits up and talks. Voyager 1 communicates using a narrow-band radio signal in the X-band, around 8.4 gigahertz. That signal is so weak by the time it reaches Earth that the Deep Space Network's 70-meter dishes detected at less than a billionth of a watt. To make this work, the spacecraft must keep its antenna aligned to within a fraction of a degree. The AACS uses tiny hydrazine thrusters to make minute corrections, guided by gyroscopes and sun and star sensors. When the AACS telemetry went weird, one fear was that the system might start pointing the antenna away from Earth. If that happened, the signal could fade below detectability, and Voyager 1 would effectively vanish. Engineers eventually discovered that the AACS was sending its data through the wrong onboard computer, one that had failed years earlier and was corrupting the telemetry. The fix was almost absurdly delicate. Send a command to a 46-year-old spacecraft across 24 billion kilometers, telling it which internal data bus to use. The round-trip light time was about 45 hours, so every test took nearly 2 days. When the corrected data finally came back clean, there was a collective sigh of relief. But the incident raised a deeper question. How many more such glitches can Voyager survive as its systems age and its power dwindles? That power comes from 3 RTGs, which convert heat from the radioactive decay of plutonium-238 into electricity. At launch, they produced about 470 watts. Today, they're down to roughly half that, and they lose about 4 watts every year. To keep the spacecraft alive, NASA has been systematically shutting down instruments and heaters. Some components now operate far below their original design temperatures, in a cold vacuum where metal can become brittle and electronics drift out of spec. Cosmic rays, high-energy particles constantly bombarding the spacecraft, can flip bits in memory or slowly damage circuits. Any of these effects could be behind the strange data, and diagnosing them from Earth is like trying to repair a watch by shouting at it from across a football field. Despite all this, Voyager 1 is doing science no other probe can. In 2012, it crossed the heliopause, the boundary where the solar wind is finally overpowered by the interstellar medium. Inside the heliosphere, the sun's magnetic field and charged particles dominate. Outside, the spacecraft is bathed in plasma and magnetic fields that come from the galaxy itself. Voyager's instruments have measured a sharp increase in galactic cosmic rays, a change in magnetic field direction, and a denser, colder plasma than expected. These data help refine models of how our star carves out a bubble in the interstellar medium, and how that bubble shields planets from some of the most energetic particles in the universe. This matters directly to you, sitting on Earth. The heliosphere acts as a kind of cosmic weather shield. When it's strong, fewer galactic cosmic rays penetrate into the inner solar system. When it's weak or compressed, more get through, potentially affecting satellite electronics, astronaut health, and even, over long timescales, atmospheric chemistry. Voyager 1's measurements of particle flux and magnetic turbulence at the edge of the heliosphere give us a ground truth for models that predict how this shield behaves as the Sun orbits the galaxy, passes through denser interstellar clouds, or encounters shock waves from ancient supernovae. In a sense, Voyager is our first weather station in the space between stars. The strange data episodes also force engineers to push the limits of deep space operations. Commands must be ultra-compact because the data rate is painfully slow, often just a few hundred bits per second. Every instruction is checked and rechecked because a single wrong command could switch off a critical system with no way to recover. When a new anomaly appears, teams simulate Voyager's hardware with decades-old documentation, then craft minimal interventions, reroute this data stream, power cycle that instrument, change a software flag that hasn't been touched since the 1980s. Each successful fix teaches us how to run future interstellar probes that might need to operate autonomously for centuries. But time is running out. Sometime in the early 2030s, the RTGs will no longer provide enough power even for the core systems. Instruments will go dark one by one. Eventually, the transmitter will fall silent. After that, Voyager 1 will continue coasting through the galaxy, frozen and blind, but still carrying the golden record. In about 40,000 years, it will pass within roughly 1.6 light-years of a star in the constellation Camelopardalis. In 1 billion years, the continents on Earth will have shifted, our languages will have mutated beyond recognition, and yet this tiny artifact of our species will still be out there, an unpowered archive drifting in the interstellar night. So the biggest open question isn't just what's wrong with Voyager 1's data, it's whether we can keep listening long enough to learn everything it has to tell us about the edge of the Sun's domain. Are the glitches we're seeing the first signs of a graceful old age, or hints of some interstellar environment we don't yet fully understand? When the last bit of data finally arrives, it will mark the end of humanity's first physical contact with interstellar space. Until then, we keep whispering into the dark and waiting for the faint echo. And as long as that echo returns, Terra Nova will be here to help you decode it.